And welcome back. We are now in section 1.6 on angles of elevation and depression. Angles of elevation and depression are nothing new. It's just a definition of something old. So quite often when you are dealing with angles, you'll have something like this. That's an angle, perfectly valid angle. An angle of depression always has one side horizontal and the other side lifted up. So that from this angle here, one side's horizontal and you lift, you elevate. Angle of elevation. This is an angle of elevation. An angle of depression also always has one side horizontal and the other side goes down. An angle of depression. So you have two and you drop. That's an angle of depression. In both cases, one of the sides must be horizontal. So if you recall in the last section, there was the problem where the girl was looking at a tree and she was off here and she looked at the top of the tree and she formed an angle with the horizontal. This here would be an angle of elevation. This one down here, angle of elevation, because one side is horizontal and the other side is lifted. Other than that, they're just angles. And as such, all the stuff that we've been using, SOHCAHTOA, the Pythagorean theorem, assuming it's a right triangle, we can continue to use. So let's jump right into example 18 on page 35. It says a ramp is to be constructed to give wheelchair access to a door of a house, 1.35 meters above the ground. So here's your house, and apparently the door of the house is off the ground. I guess maybe there's steps leading up to it. And we want to make a ramp. I'm not going to put it over the drawing of the house. It'd be a little confusing. But we want to make a ramp B, C, and then we have a horizontal. And then there's the height. And this point here, this is 1.35 meters. It says safety regulations require that the angle of the ramp, which we'll call theta, be less than 8 degrees. So we have the condition that theta must be less than 8 degrees. We don't know what theta is, but it's less than 8 degrees. So part A, it says draw a diagram and label the vertices and the sides. Well, we already have B and C, so let's label the other one as A. Let's make that a 90-degree angle because it's vertical. And this here is the ramp, and this here is the ground. So that's part A. Part B, let's do some math. Find the length of the ramp BC, where angle ABC, start from A to B to C, ABC, this angle here, theta in our nomenclature, is 8 degrees. So assume theta is equal to 8 degrees. Now this is actually quite interesting because it said that the angle of the ramp has to be less than 8 degrees. So I guess this is the upper bound that we've talked about before, that this is worst case scenario. This is the border of what's allowed and what's not allowed. And we want the length of the ramp BC. Well, it's a right triangle. We can't use the Pythagorean theorem because we only have one side, so we have to go to SOHCAHTOA. So we want the hypotenuse, opposite hypotenuse. Ooh, that's sine. So sine of 8 degrees equals opposite over, I'll use R for ramp. Remember, when you have two fractions that are equal to each other, and you can imagine sine of 8 degrees over 1 is a fraction. You can put it in here if you like. You are allowed to switch top left and bottom right. They can just straight up switch. So I can rewrite this as R equals 1.35 over sine of 8 degrees. If you don't believe me, you can always go through the process of cross multiplication. R times sine 8 degrees equals 1.35. And divide both sides by sine 8.8 degrees. Hey, look at that, we're in the same place. So 1.35 divided by sine of 8 degrees. And this gives us 2 sig figs, because they don't say otherwise, 9.70. And we have units of meters. Part C says, find the distance AB, that's the ground, giving your answer to 1 decimal place. So it was 3 sig figs for the last one, but now they're saying 1 decimal place. Give your answer to 1 decimal place. Okay, well, AB. Of course, we can use the Pythagorean theorem now because we have 2 of the 3 sides, but let's use SOHCAHTOA anyways. We want the ground, we have the opposite, ground, opposite adjacent, that's tangent. So tangent of 8 degrees equals the opposite over G for grounds. Same logic, G equals 1.35 over tangent of 8 degrees. 1.35 divided by tangent of 8 degrees gives me to 1 decimal place, 9.6 meters. But, not but, it's another mistake in the book, because when you look at their answer, it says 9.61 meters, 3 significant figures. But the question specifically says giving your answer to 1 decimal place. So it's another mistake. Trust me, we're going to find lots of them. They're all over the place. Next example, number 19 on page 36. From his studio window at point A, which is 6.50 meters above the grounds. So here is the grounds, and this distance here is 6.50 meters. Tomchik, T-O-M-C-H-I-K, I hope I pronounced that correct. Tomchik views the top and the base of a building on the opposite side of the street. So here's a building on the opposite side of the street. And let's lower it so that it's not levitating. Okay. And Tomchik views the top. So he looks up, or she, I'm not even sure, probably he. And he looks down. The top and the bottom. The angle of elevation and depression. Well, angle of elevation and depression requires a horizontal. So let's throw in the horizontal. The angle of elevation and depression are 55 degrees and 18 degrees respectively. Find the height of the building he is viewing, giving your answer correct to 2 decimal places. So we'll see if they do that part correct. So we want the height of the building. This part here is 6.50 meters because it's parallel and it's the same line segment, right? It's just, we take this part right here, which we know is 6.50, and this is a perfect copy of that, even though my line is not really horizontal. Sorry, my OCD is going to make me redo this one. Now let's get horizontal there. Hopefully that's better. So that's 6.50 meters. We just need this guy here, X. Now, when I look at that upper triangle, I have an angle. I'm looking for X. I have one angle. That's it. That's not enough information. Pythagorean theorem, need 2 sides. I only have 1. No, sorry, don't even have any. SOHCAHTOA, need either 2 sides or an angle and a side. I have all 3 angles because once you know one angle and you have 90, we have the other one. But with no information about sines, nothing I can do. So somewhere in this problem, there has to be enough information to find a side. So what else do I know? Well, I know something about the bottom triangle. And I have an angle and a side for that one. Hey, okay, so let's call this Y. So angle 18 degrees, this is still 90, so it's a 90-degree triangle. I can use SOHCAHTOA, opposite 6.5, adjacent is Y, opposite adjacent, that's tangent. So tangent of 18 degrees equals opposite, which is 6.5, over adjacent, which is Y. So that same logic as above, Y equals 6.5 over tangent of 18 degrees. I'm not going to use my calculator yet because I'm not done with the problem. I'm just going to keep that. That's my Y. Any problem later, any formula later in this problem that requires Y, I know I have it. So Y is currently known. Since Y is currently known, I can go to the upper triangle. I have the angle, I have y, I need x, opposite adjacent, that's tangent again. So tangent of 55 degrees equals opposite over adjacent. In this case, I need x, so x equals y times tangent of 55 degrees. But I have y, it's 6.5 over tangent of 18 degrees times tangent 55 degrees. So now I have y, sorry, now I have x. And what is the height of the building? The height is x plus 6.5. So it's going to be 6.5 tangent 55 degrees over tangent of 18 degrees plus 6.5. And I can factor out the 6.5, leaving me with tangent 55 degrees over tangent of 18 degrees plus 1. And that's as simplified as I can get. So at this point, tangent 55 divided by tangent of 18, all plus 1. Calculate that, multiply by 6.5. And to two significant figures, I get 35.07, 35.071 meters. That is the answer that the book has. So congratulations, we got it correct. And they got it correct. I think that's actually more of a congratulations. So let's jump now into exercise 1I. Exercise 1I. Okay, so there's 5 questions here. And again, as always, get the question, pause, solve, check. So question number 1. The angle of depression from the top of a cliff. Okay, we have a cliff. And here we have whatever is out there. So the angle of elevation from the top of a cliff, this is our starting point, to a boat at sea. So here's a boat. And I don't know how to draw a boat. So I don't know. Is there like a flag there? Is that a boat? Put a person in there. Okay, that's the boat. Is 17 degrees. So that means from the horizontal, because angles of elevation and depression always get a horizontal, to the boats, and I assume they mean the bottom of the boats, is 17 degrees. That's an angle of depression of 17 degrees. The boat is 450 meters from shore. The boat is 450 meters from shore. So this distance here is 450 meters. Of course, since the upper triangle is the one that I'm going to use, I also know that the top here is 450 meters. Part A, draw a diagram representing the situation. Okay, I gave you A, but now for you, for part B, find the height of the cliff. Giving your answer rounded to the nearest meter. Pause, solve, check. So we want the height of the cliff, H. Height of the cliff, H, is also this part over there. It's also the same height. Angle, right triangle, SOHCAHTOA, one opposite, have adjacent, that's tangent. So tangent of 17 degrees equals opposite over adjacent. So H equals 450 times tangent 17 degrees to the nearest meter is 138 meters. Question number 2. A family wants to buy an awning for a French window. So here is their window. And they want to buy an awning that will be long enough to keep out the sun when it's the highest point of the sky. So the sun is yellow. So here's the sun, the highest point of the sky, not from the scale. And we want to have an awning that will keep out the sun. The height of the French window is 2.80 meters. So the height of the French window, 2.80 meters. The angle of elevation of the sun from this point to the bottom of the window is 70 degrees. That was a horribly phrased sentence. The angle of elevation from the bottom of the window to the sun, that makes more sense. We'll check if the answer is correct. But the angle of elevation from the bottom of the window to the sun is 70 degrees. I don't got to go all the way to the sun. I just need to go in that direction. That's 70 degrees. because the awning is going to be 90 degrees to the window. So the awning is going to come out like this. So I just need the awning to be just far enough out that the sun rays cannot hit the bottom of the window. How long should the awning be? What is X? And write your answer to 2 decimal places. Okay, well, we want one side of a right triangle. We only have one other side, so I can't use the Pythagorean theorem. I want to use SOHCAHTOA, but I need an angle. My 70 degrees down there is actually outside the triangle. But if you know your geometry, you know that this here must be 20 degrees, so that it adds to 90. Now that I have that, 20 degrees, I have adjacent, I want opposite, adjacent, that's tangent. So tangent of 20 degrees equals opposite over adjacent. Therefore, X is equal to 2.8 times tangent of 20 degrees. Write your answer to 2 decimal places. That's 1.02, and the units are meters. Question number 3. Scientists measure the depths of lunar craters by measuring the length of the shadow cast by the edge of the crater using photographs. In a photograph, the length of the shadow cast by the edge. So here's the crater. The crater, you know, it's going for a while. And the length of a shadow cast by the edge of the crater, specifically the Moltke crater, is about 606 meters. So we have a shadow here that's about 606 meters long. And that's the length of the shadow cast by the edge of this crater. The sun's angle of elevation, because what casts shadows? The sun casts shadows. So here's the sun's angle of elevation, and by that they mean the angle of elevation to the sun is 65 degrees. This is obviously not drawn to scale because that angle is very small. Find the depth of the crater. What is X? How deep is the crater? Okay, well, right triangle. We have adjacent, we want opposite. As before, that is tangent. Tangent 65 degrees is opposite over adjacent. So we get 606 times tangent 65. And it says, give your answer to the nearest meter. So that will be 1,300 meters. Sometimes the questions are hard to translate into picture. But once you have the picture, then the math is easy, or should be easy. So get practice on reading and translating it so you can see what's going on. Number 4, the height of a building is 72 meters. Well, that one is a no-brainer. The height of a building is 72 meters. Find the angle of elevation from a point on the ground that is 55 meters away. So here's a point on the ground that is 55 meters away. So I drew it. My initial ground was just longer than it had to be. Well, let's get rid of it. Ain't technology grand. So find the angle of elevation from a point on the ground that is 55 meters from the base of the building. So presumably they want the angle of elevation to the top. So they want to know this angle here. They want theta. Well, I put 72 meters on the other side, but it certainly can be on that side as well. So angle adjacent opposite, tangent again. Tangent of theta equals opposite over adjacent. That's great, but I want theta itself. How do I get theta itself from adjacent, opposite and adjacent? Well, we've done that before. It's the arctangent or the inverse tangent. So inverse tangent, 72 over 55. And that gives us no instructions, so it'll be to 3 6 figs, 52.6 degrees. And then finally, we have question number 5. From a boat 160 meters out to sea. So here's the boat, which is over here. That's my boat again with the person in there. 160 meters out to sea. The angle of elevation to the coast is 18 degrees. Okay, so angle of elevation is 18 degrees. The angle of elevation to the top of a lighthouse on the coast. Ooh, we have a lighthouse here. I don't even know what color to use for, I don't even know, how do I make a lighthouse? Okay, that's my lighthouse. And it's got a beacon there, and the beacon is, that's my lighthouse. Okay. The angle of elevation to the top of the lighthouse. Well, remember, angle of elevation must always have one side horizontal, which means the 22-degree angle is this entire thing. The angle of elevation to the top of the lighthouse on the coast is 22 degrees. Notice that I kind of put arrows on the end of that arc, so you know where the angle starts and stops. You don't think it's just the bottom, you don't think it's just the top, but rather it's the whole thing. I could do the same thing for the red one here, the 18 degrees, even though it's not really necessary, but nothing wrong with it. So A, draw a diagram representing the situation, and then B, find the height of the lighthouse. So pause, attempt, check. So there's 2 triangles here. We're going to call X, that's going to be the height of the bottom triangle. And we're going to call Y, this is the height of the big triangle. And what we're looking for the height of the lighthouse is then Y minus X. The whole height minus the bottom height. So we're going to find X and Y independently and then subtract. So let's find X first. X is the height of the lower triangle. We have the angle, it's 90 degrees, of course. We have the angle, we have adjacent. We want opposites, that's tangent again. Tangent of 18 degrees equals opposite over adjacent. So X, when we'll need it, is 160 tangents of 18 degrees. By exactly the same logic, we have tangent of 22 degrees equals Y over 160. So that Y equals 160 tangent of 22 degrees. So what is Y minus X, what we're looking for? It's 160, which I can factor out, and then I get tangent of 22 degrees minus tangent of 18 degrees. At this point, take out my calculator. Tangent 22 minus tangent 18. Compute that, multiply by 160. And this gives me, and do they say sig figs? They do not, so 3, so 12.7, and the units are meters. So that takes us to the, excuse me, that takes us to the end of the exercises. So now let us continue for the second portion of section 1.6, where we have a new formula, and it's the arc length formula. Formula of an arc. This is kind of important. Plays a role in lots of questions. And the question is as follows. If you have a circle and you get the center there, and you take 2 random points on the circle and you connect along the circle, our goal is to find the arc length of this. They don't have a symbol for it. Traditionally, we use the letter S for arc length. The book doesn't have a symbol, it just gives you a formula for it. But the question is, if I know the radii, if I know the radiuses R, and I know that the angle is alpha, then the question becomes, can I use that information to find the length of the arc? And the answer is yes. And rather than just giving you the answer, I'm going to explain why the answer is what it is. And it has to do with proportions. If I look at the entire circle, then the arc for the entire circle is just a circumference, which hopefully you know, or at least if you don't, it's on the formula sheet, is 2 pi r. So 2 pi r, which is the length of the entire circle, is to 360 degrees, which is the angle for the entire circle, as s, which is the arc of a portion of the circle, is to alpha, which is the angle for the portion of the circle. So we have this relationship here between them. And now all we have to do is solve for s. So s equals, you know what? S equals, we can cross multiply here. We get 2 pi r alpha over 360 degrees. And if you want to do 2 over 360, you can reduce it to pi r alpha over 180 degrees, which means you have to know alpha, you have to know r, you plug them in, and there's your formula. The arc length formula. Now, this formula is in the formula book, so you don't have to memorize it, but it's always a nice idea to see where it comes from. So let's do a quick example. Find the length of the arc of a circle with radius 2 centimeters and central angle alpha 120 degrees. Of course, it is important, so I should specify this, that it has to be a central angle. The angle has to be from the center of the circle. If you take a circle, I'll erase this in a minute just to illustrate, and you pick some random points, not the center. You pick some random point to try to find the arc, where the center is here, then this angle is not correct. You can't just use any random angle you want. It has to be the central angle. So they have to give you that either in words by calling it a central angle or in a picture by having it occur at the center. Otherwise, you can't do anything. So what is the arc length? Well, let's go right to the formula. Pi times 2 centimeters times the angle, which is 120 degrees, divided by 180 degrees. The degrees cancel so that we're left with units of centimeters. And we have pi times 2 times 120 divided by 180. And we get to 3 significant figures. We get 4.19 centimeters. And that's it. The book, and I'm looking at the answer, the book says, hey, you can also do it this way. And while it's true, there are other ways of doing it. I don't necessarily see the advantage of that. But essentially, just to tell you what they do, is they say 120 degrees. Well, 120 degrees, that's a third of a circle, because a circle is 360 degrees. So just take the circumference and divide by 3. Take 2 pi r, the circumference, and divide by 3. Well, okay, if r is 2, as it is here, then it should just be 2 pi times 2 over 3. But that's just essentially the same thing that we have, because if you look at what we have, the 2 and the 2, of course, match. The pi and the pi, of course, match, and you're left with just 2 over 3, which is the same thing as 120 over 180. The formula that we derived has already taken this into account. Can you do it this way? Sure. Is it faster? I don't see it, but hey, if it's faster for you, knock yourself out. Just get the right answer. That's all I care about. So let's jump ahead now to exercise 1J. And there's 4 questions here, and this will finish the chapter, or at least the portion of the chapter dealing with instruction. There are some, review exercises at the end and stuff like that. Question 1. Determine the length of each arc with radius r and central angle alpha given below. So part A, r this time is lowercase. Doesn't really make a difference. Oh, it's always been lowercase in the book. I use capital. Who cares? Same thing. R equals 5 centimeters, alpha equals 70 degrees. Well, let's go directly to your formula. Pi times 5 times 70 divided by 180. 2 decimal places, so that's 6.11 units centimeters. S equals. B, R equals 4 centimeters, alpha equals 45 degrees. Back to your formula. Pi times 4 times 45 divided by 180. This one is to 2 decimal places again, 3.14 centimeters. Oh, 3.14, that sounds a lot like pi. And indeed, it is. On my calculator, I have 3.14159.265 and so on. So it is pi. And you might say, well, why should it be that way? Well, if you think about it, if you plug in alpha is 45, 45 over 180 is 1/4. And then if you multiply by 4, it becomes 1, and you're left with just pi. So sometimes things work out algebraically that you might not see otherwise. C, R equals 10.5 centimeters with an alpha of 130 degrees. Same thing. Pi times 10.5 times 130 divided by 180 gives me 2 decimal places, 23.82 centimeters. Question number 2. A clock is circular in shape. Okay, well, a circle. With a diameter, D equals 25 centimeters. Find the length of the arc between the markings 12, well, 12 is here at the top, and 5, which is here somewhere, rounded to the nearest tenth of a centimeter. So pause, solve, and hopefully now we can check. So if we draw this, because we need a central angle, we need 2 things. We need the radius. Well, the diameter is 12 and 25. The radius is 12.5 centimeters. And now we need the angle. Well, assuming the clock is correct, then what is the angle here? Well, half circle is 180 degrees. So this is 5/6 of a half circle because it's 5 hours out of 6 hours. So alpha equals 5/6 of 180 degrees, which is 150 degrees. Every hour is 30 degrees, right? Think of it that way. 12 hours, 360 degrees, each hour, 30 degrees, 5 hours, 150 degrees. So what is the arc? S equals pi r alpha over 180 degrees. So let's make sure pi r alpha over 180 degrees, pi times 12.5 times 150 divided by 180. And this gives me an arc length of, rounded to the nearest tenth of a centimeter, 32.7 centimeters. Question number 3. The London Eye is a giant Ferris wheel in London. It is the tallest Ferris wheel in Europe with a diameter of 120, no, not centimeters, that would be kind of small, but 120 meters. So we have this Ferris wheel. The passenger capsules are attached to the circumference of the wheel, and the wheel rotates. We get a rotational speed, an angular speed of 26 centimeters per second. Every second, the wheel rotates 26 centimeters. So this one has got 3 parts. Each part, pause, solve, check. Find A, the length that a passenger capsule would travel if the wheel makes a rotation of 200 degrees. If the rotation, if alpha is 200-degree rotation, then what is the length of travel? Now you travel along the arc. Because you're traveling along the arc, we want the arc length. Well, it's pi times r, which is 60, because d is 120, so r is 60, times 200 degrees divided by 180 degrees. So pi times 60 times 200 divided by 180 gives me, in meters, equals 3 sig figs, 209 meters. B, the time in minutes that it would take for a passenger capsule to make a rotation of 200 degrees. Okay, the time in minutes. Pause. Try to solve this one. This one's a little more challenging. We have to relate time to angle. Well, we've already related angle to distance arc length. We know that 200 degrees is 209 meters. Why do I care? Because you're traveling at 26 meters per second. 26 meters per second is 0.26 meters per second. So how many seconds will it take to travel 209 meters? We just divide 209 by 209 meters divided by 0.26 meters per second. If you look at the units here, the meters cancel and the seconds flips to the top, so it's the correct units, and we get 806 to 3 sig figs, 806 seconds. But they want the time in minutes. So let's do a conversion. We know 60 seconds is 1 minute. So if I divide this by 60, I get 13.4 minutes to make a rotation of 200 degrees. And then finally, part C, the time to the nearest whole minute that it would take for a passenger capsule to make a full revolution. So we don't got to start all over again. We can do a ratio. 13.4 minutes is to 200 degrees, as the unknown amount of time is to 360 degrees, because you're traveling at a constant speed. So distance over time, or in this case, time over angle, should be the same for any size angle. And therefore, x equals 13.4 minutes times 360 divided by 200 to the nearest minute is 24 minutes. That was a nice question. It has my personal seal of approval. And then finally, last question, question number 4. A door with a width 4.20 meters has an arc as shown in the diagram. So this is what we have here. We have this, and then we have this, and this is 4.20 meters. And they tell me that this angle here is 225 degrees. They draw a dotted line across here, and they draw an arc here. Now, my arc might not be perfect, but we'll assume it's the arc of a circle. So we have these points here at the ends, and this is the picture. They draw a dot right here as well, right above this dot, which they draw over there. So this is what they draw. So again, let's read the question. A door with a width 4.20 meters has an arc as shown in the diagram. I don't really understand what door they're talking about, but let's see if we even need to worry about it. A, find the radius of the arc to the nearest centimeter. The radius of the arc to the nearest centimeter. Well, that seems easy enough. It should just be 2.10 meters, because the base is 4.20, so this is half of that. And they want it to the nearest centimeter, so that's going to be 2.10 meters is 210 centimeters. And then once I have that, they want the length of the arc to the nearest centimeter. Well, the angle of the arc is 180 degrees. I have no idea what's going on here. What is that 225 degrees in the bottom doing? I don't know what's happening here. Let's check the end of the book and see if, at least we got part A correct. So this is chapter 1.6. Chapter 1.6 is IJ. So they say the radius is 227 centimeters. So I am missing something here. I am missing something. I'm going to pause until I figure it out. And I figured it out. Okay, so this dot up here, the top dots, is not the center of the circle. The center of the circle is that one. That's the center of the circle, which means the radius is this length right here. And this is the radius. Now I do know that this is 2.10 meters. That part was correct from before. But I need R. Now, I don't know this length right here, but I do know that it makes a 90-degree angle. And if the bottom angle is 225, then the total top of that arc must be 135. This whole arc here must be 135. And I want half of that. So this angle here must be 67.5 degrees. And now that I have that angle and I have the opposite, and I want the hypotenuse, opposite hypotenuse, that's sine. So sine of 67.5 degrees equals opposite, which is 2.10 over R. So therefore, R equals 2.1 over sine of 67.5 degrees. And that does give us what's in the back of the book as 236 figs, presumably 2.27 meters or 227 centimeters. So now part B, find the length of the arc to the nearest centimeter. Well, now that I have that the radius is 227 centimeters and the angle is 135 degrees. The angle of the arc, the whole top is 135 degrees. S equals pi r alpha over 360 degrees. So take my 227, of course, with all the decimals because I'm still calculating, times 135 divided by 360. Divided by not 360, divided by 180. So divide by 180. And multiply by pi. And this gives me, to the nearest centimeter, 536 centimeters. Okay, so sometimes problems do even trip me up when it comes to understanding what's going on, but hopefully that made sense. So this takes us to the end of section 1.6. The chapter is over in regards to the material that you must know. And we'll have a couple more lectures on video for the chapter review before heading into chapter 2. See you there.